Welcome to Topology Lesson 19 on topological spaces. In this lesson, I'm going to talk about compactness and also connected topological spaces or subsets thereof. Recall from our lessons on metric spaces that the definition of compactness for a metric space relied solely on open sets and not the metric associated with the metric space. We can define compactness for topological spaces in the same way, i.e. topological space is compact if every open cover has a finite subcover. And I copied the definition of open cover down here just to remind you. So let's read that again. An open cover of a topological space X is a collection of open sets of X whose union equals X. So that's pretty straightforward. Then a subcover, an open cover of X is a subset of the sets in the open cover. So what we're saying here is for any open cover, there's a finite subcover. What we're not saying is that there's a finite subcover. That's always true. You can always take the entire topological space and that'll cover itself, and that would be a finite cover. But what we're saying is if you have an open cover, any open cover, you can always pick a finite number of those and still cover the space. And we have another definition here. A subset Y of a topological space X is compact. A subset of X. If Y is compact in the relative topology, it inherits from X. Remember, we defined that earlier. This happens if and only if Y has the following property. If U sub A, the collection of sets U sub A, where little a is an element of some indexing set A, possibly uncountable, collection of open sets in X that covers Y, then there is a finite subcollection of U sub A sets that covers Y. Okay, so that looks very much like the definition of compact for the entire topological space. The only wrinkle here is the using this relative topology. The definition of compactness for topological spaces is cast only in terms of set theory ideas, unions and set intersections, and the openness of sets. A homeomorphism being a one-to-one and onto function preserves unions and inclusions, and it preserves openness by definition. Thus, a homeomorphism between topological spaces preserves compactness. So if you have a homeomorphism between topological space X and Y, if X is compact, so is Y. If X is not compact, then Y is in either, and the same would hold for the subsets over the homeomorphism mapping. We have a couple theorems on this slide concerning compactness. The first one is a finite union of compact subsets of a topological space is compact. So let Y sub I be our finite collection of compact subsets of our topological space X, and let Y equal the union of these compact subsets. And we want to show that this union is compact. That's basically the theorem. So let U sub A, for little a an element of some indexing set A, possibly uncountable, be a collection of open sets of X that covers Y, and thus covers each Y sub I. Then for each I from 1 to n, there is a finite subcollection of the U sub A sets that covers Y sub I, since the Y sub I sets are compact. The union of each of the finite subcovers for the Y sub i's from I1 to n forms a finite subcover for Y. So that gives us the proof of our theorem. Okay, then we have another theorem. A closed subspace Y of a compact topological space X is compact. So closed in a compact topological space implies compact again. We can prove that. Let U sub A be a collection of open subsets of X that covers Y. Since Y is closed, its complement is open. Thus, this collection of elements here, this set here, U sub A union was the complement of Y. If you take all of these, is an open cover for X. If you're just combining the cover for Y, and then the union was the complement in each case. So you still have a cover for the entire X. And since X is compact, there is a finite sub collection from this set here that covers X, and then the corresponding U sub A's in this finite sub collection covers Y, and thus Y is compact. We have two theorems concerning compact subsets of a topological space and the Hausdorff property. The first theorem, let Y be a compact subset of a Hausdorff space X. For each X in the complement of Y, there exist disjoint neighborhoods U of X and V of Y. In terms of a proof, since X has the Hausdorff property, for each Y an element of Y, there exist disjoint open neighborhoods of X and Y. We'll call them U sub Y and V sub Y, since these depend on, there's a different one for each Y. The open sets V sub Y for every Y an element of Y form a cover of Y. And since Y is compact, there is a finite subcover. So just a finite number of these V sub Y's, which I've listed here and I've called them V. Taking the corresponding U sub Yi for X relative to Y sub I, in other words, the U sub Y's corresponding to these. And then we take the intersection of those and set that equal to U. This is an open neighborhood of X that is disjoint from V. So we have the requirements of our theorem proven here. So just one note, we needed Y to be compact because we wanted to get a finite cover. And the reason we wanted a finite cover is when we took the corresponding U's, we wanted to take the intersection. And if you recall, an infinite intersection of open sets is not necessarily open. So we needed a finite collection here, which is what we got because of the compactness of Y. Okay, so the second theorem, a compact subset of a Hausdorff space is closed. We'll use this theorem to prove it. By theorem 108, for every X in the complement, there are disjoint open neighborhoods of X and Y. So the complement of Y is open, being the union of open sets, and thus Y is closed. We have another theorem here concerning Hausdorff, normal, and compactness. Every compact Hausdorff space is normal. Just to remind us from our previous lesson, I've copied the definition of normal down here. Normal, topological space is normal if any two disjoint closed subsets of X are separated by neighborhoods. So we'll start the proof, by taking disjoint closed subsets S and T from our compact Hausdorff space X, and we want to show that they can be separated by neighborhoods. So we're going to construct a neighborhood about S and T that are distinct. So we know by theorem 107, which we proved a few slides back, that S and T are both compact since they're closed, and they're in a compact space. So by theorem 108, for each T, little t, and capital T, there exists a disjoint neighborhood U sub T of T and V sub T of S. Disjoint neighborhood. So the construction is these are disjoint. The open sets U sub T provide a cover for T, capital T. Since T is compact, it has a finite subcover. So we'll just let that equal U. These are these U's here that I'm pointing to are from the cover. It's finite subcover. We'll let that equal U, and then we'll take the corresponding V sub T sub 1 and so on. We'll take the intersection of all those. We'll let that equal V. Then S is our closed set. S is a subset of V, and by construction, V intersection U is empty. Thus, X is normal because we now have found two our sets U and V that are neighborhoods of T and S and are separate or disjoint in separating the two closed sets S and T. The following theorem relates continuous functions and compactness. Let F be a continuous function from a compact topological space X to a topological space Y, then F of X, in other words, all the elements in X mapped to Y by F, which could be a subset of Y, is a compact subset of Y. So if U sub A is an open cover of F of X, then the inverse mapping F inverse of the U sub A's is an open cover of X. And since X is compact, we can find the finite subcover. So we have that listed here, and this would equal X. Then take F of X on both sides of this, and we get F of X equals the union of these finite number of U sub A I. In other words, the F of X has a finite subcover given any open cover that we started with, and thus F of X is compact. Let's talk about connectedness. Intuitively, a topological space is connected if it's all in one piece. This leads one to conclude that a topological space is disconnected if it can be written as the union of two non-empty separated pieces. To make this more precise, we need to determine what's meant by separated. And you can get in some issues here if you're not careful. For example, we correctly think of the real line, the real numbers, as connected, even though it can be written as the union of two pieces, right? The interval from minus infinity to 1 inclusive, and then from 1 to plus infinity, not including 1, are disjoint, but we don't think of the real numbers as being discontinuous or unconnected. So we must need something more than this intuitive sense that we've talked about up here. So separated must mean something more than disjoint. In fact, we need to use the definition of separated state sets that we stated earlier. Two subsets of a topological space are separated if each is disjoint from the closure of the other. So that's the key thing here. A topological space is connected if it cannot be expressed as the union of two non-empty subsets that are both open and closed and separated from each other. On the other hand, a topological space is disconnected if there are closed and open subsets U and V of X such that the union of U and V equals X. U and V are both non-empty. And then the tricky part here is this statement, and it's saying that U does not intersect the closure of V, and V does not intersect the closure of U. That's the key condition. We have some conditions that are equivalent to connected. The first one is the actual definition we stated on the previous slide. X is connected, i.e. it cannot be divided into two disjoint non-empty open sets. Then that's equivalent to the only subsets of X which are both open and closed. They use the term clopen. I've seen this in the literature. Are X in the empty set. The only subsets of X which with empty boundaries are X and the empty set. X cannot be written as the union of two non-empty separated sets for which each is disjoint from the other's closure. Remember, that was the condition we showed about being disconnected. All continuous functions from x to the set 0, 1 are constant, where 0, 1 is the 2-point space endowed with the discrete topology. And I put a reference down here where I got these equivalent statements. It's the Wikipedia article entitled Connected Space. Let's look at a few examples. I've copied the definition of disconnected here because we're going to need that. It's from the few slides back. So our first example is the real numbers minus the point 0, and that's disconnected since we can write it as the union of two separated open and closed sets, the interval from minus infinity to 0, union with the interval from 0 to infinity. So these sets are disjoint, and you notice the closures, this property down here, if you take the closure of this, it doesn't intersect this, and vice versa. The second example is the closed interval from minus 1 to 1. This is as a subspace topology of the real numbers. So that's connected, as you might expect. It looks connected, right? But in terms of the definitions, just to clarify some things here, if you take the interval from minus 1 to 0, excluding 0, and then the closed interval from 0 to 1, you might think that these fit the definition of disconnected here. But the problem is the closures are not disjoint. They have to be disjoint closures in order to say that the set is disconnected. And you notice here the closure of this one on the left intersects this. And so we don't fit the definition for disconnected here. Now, if we take the union of minus 1 to 0 and 0 to 1, you notice the 0 is missing here. That is disconnected, and we can write that as the union of two sets that are both open and closed. Now, that may be a little confusing, so let me explain that. These are open and closed in the topology, the subspace topology was this set here from minus 1 to 0, excluding 0, union with 0 to 1. They're open and closed there because the closure of minus 1, 0 in this subspace is minus 1 to 0. The 0 is not included. It's just not a member of the subspace. And the same thing here. If you take the closure of this, you get the same interval. You don't include 0 because, again, 0 is excluded from the subspace. So each of these are both open and closed. They equal their closure. This equals its closure, and so it's closed, and that means its complement, which is this, is open, and vice versa. So these are both open and closed. And finally, we have another example, which is the interval 1 to 2. Union was just the point 5, and that's disconnected. And as you might expect, in this subspace, 1 to 2 is equals its closure because you don't have the points 1 and 2 to add in. They're not in the subspace. So this equals its closure, which means it's closed, and its complement is open, so 5 is open. But we know singletons are closed, and so its complement would be open. So this is open. So in other words, we have this subspace as the union of sets that are open and closed. In other words, these two components. Okay, so it's pretty much what you would expect when you look at some of these. You know, if there's a point missing like this one here, you would expect it to be disconnected. And if it's continuous like this one here, you would expect it to be connected. Again, here these two, I guess, are similar. This is just going to minus and plus infinity, but you have the same problem with 0 being missing. We have a few more definitions here concerning connectedness. The first one is something called path connectedness. It's a stronger notion than connectedness since it requires a path. But if you're path connected, then you're also connected as a topological space, as we defined connectedness previously. So a path from a point X to a point Y is in a topological space is a continuous function f from the unit interval 0, 1 into X, with f of 0 equaling X and f of 1 equaling Y. A path component of X is an equivalence class of X under the equivalence relation, which makes X equivalent to Y if there is a path from X to Y. The space X is said to be path connected, and there's other terms are used also, pathwise connected or zero connected, if there is exactly one path component. In other words, all the points in your topological space have you can get from one point to another with a path. So for non-empty spaces, this is equivalent to the statement there is a path joining any 2 points, which is what I was just trying to say in the previous sentence. And then we have another definition here. A topological space is said to be simply connected if there is a path connected and if it is path connected, and every path between 2 points can be continuously transformed into any other such path while preserving the 2 endpoints in question. So intuitively, this corresponds to a space that has no disjoint parts and no holes that go completely through it, because 2 paths going around different sides of a hole cannot be continuously transformed into the other. So we'll see a few examples of these and connected in the next slide. We have a few examples on the right of this slide, actually 5 examples. I'll go through each one. The regions under consideration are ones that are in color. So it's red, then this pink, purplish color, and this brownish yellow, and then this brownish orange color here, and then the green. It's not the white areas. Those are excluded from the particular topological spaces that we're representing here. So for each one, we'll go through whether they're connected, path connected, and simply connected, should I say, or simply connected. So, and remember, these build on each other. So if you're not connected, then you can't be path connected or simply connected. And if you're connected and path connected, and not path connected, for example, then you can't be simply connected. So keep that in mind. So let's start with the first one in red. So this is connected. It's path connected. You can get between any 2 points here with a path. And if you have multiple paths between 2 points, you can deform one into the other. So that has all 3 of the properties. The second one here is kind of a bit odd. It has this line going to the edge, but it's connected. You can go between and path connected. So you can get between any 2 points, which I'm showing here, this point here and this point here. You can get a path between them. If you have 2 paths between any 2 points, I could move these around. You can deform one into the other. You can see how the yellow could just be stretched out to be the blue one here. So it's simply connected also. And it's of genus 0. Because of this line here, there's really no, you can just kind of compress this whole thing into that line, and then that's not really a hole in this topological space. The third one is connected, and it's also path connected. You can get between any 2 points with the path, but it's not simply connected, because if you notice here, these 2 paths, the black, or I think it's black, this black path and this green path, you can't deform one into the other because of this hole. So it's not simply connected, and it's of genus 1 because it has one hole in it. Okay, then this one here, the brownish orange color, that's connected. You can go between any 2 points. You can take something like, and it's path connected. It's not simply connected because you could do the same type of thing here with going 2 different paths on either side of, say, this one here, and there's no way to deform one path into the other. So this is not simply connected. Okay, then the last one, these, and it's genus 4, by the way, this one here, you have 4 holes in it. Then the last one, the green, these 4 green things, they're not even connected, which means it can't be path connected, and since it's not path connected, it can't be simply connected. So this doesn't fit any of our definitions of connected, unless you want to consider a subspace. Then these individual subspaces are connected, and path connected, and simply connected. But the whole topological space, these 4 green areas, are not connected at all. Okay, so that's the last lecture in the our overview of topological spaces. I emphasize it is an overview. There's a ton of more information on topology, but hopefully this gets you started. I'm going to do one more series of lessons related to my book, Mathematical Vignettes 3, and that's on non-Euclidean geometry. So that'll follow after, the first one will follow after this lesson.